So if Professor Pillai, if you're ready, you can.
Thank you. So this, I'm going to talk about how to make concrete structures resilient against corrosive environments. In the last slide, Professor Barsingh, he mentioned about that he didn't cover about corrosion, so I'm going to fill that gap here. And this is a work by me and my students, Deepak, Sripriya, and Diana. So looking at, but more on using the input from them and looking beyond for future what we would be probably doing. Yeah, so the outline of my presentation is, first I will talk about the context of chloride-induced corrosion when we talk about resilience, and then service life parameters, and then service life of structures, structures with specifically uncoated and coated rebar systems, and also pre-stressed concrete strands. So that will be the boundary for today's discussion. And then also I will highlight some of the things about what is expected from these structures at the time of their design, and what is a ground reality based on some of the lab experiments which we have done and the analysis based on the data collected. And then suitability of preventive measures to extend residual service life, or rather how to make the structures more resilient against corrosive environments. And the two methods which we are going to talk about is how to look at the concrete surface coating, how effective they can be, and also looking at cathodic protection systems. So the resilience of construction and infrastructure can be considered as this. I just copied from the brochure of this program, which is, so because mostly we talk about other immediate actions from the environment to the structures, but here we are looking at more of a slow reaction. So how this context is the evolution in the face of challenges. The challenges here is chloride-induced corrosion, and through the pre-planned strategies or simple improvisation, which I'm going to call as the remedial measures which we are going to talk about. So this is a pie chart showing how severe the or the distribution of the causes of structural failures. Okay, and here we have very clearly materials play a significant role in causing the structural failures. But often we don't recognize it because it's a slow process, whereas we give more importance when structural reasons or other construction related reasons, then you get more importance. But the materials has a significant role, especially their durability properties have significant role in defining the service life and how we can ensure the structures from failure. So the structural and exposure conditions which I am going to talk about today is mainly about the coastal structures. So we have many structures along the coast. As you can see on the pictures at the bottom, many new bridges are coming up, and then also we have new ports, highways, and a lot of housing or building infrastructure, both commercial and residential. So it's a huge inventory of concrete structures which are lying on the coast. So whatever I'm going to talk about here, even though I'm going to talk about one case study which is on a bridge, it's applicable to buildings or any of the concrete infrastructure which we have along the coast. So the main problem, as shown in the previous slide, the pie chart, is the quality of materials used are later found to be inferior than expected. What that means is at the time of design, we have built a lot of structures thinking that the materials are going to behave or resist corrosion in a better way. However, the test results which we have done are indicating that they may not be performing as expected. I'm going to show some results later. And also we have exposure conditions that are very severe today, and in future it may be more severe. Like, if you're talking about some of these structures which you see on the picture, they are designed for 100+ years of life. So we also have to think about how severe the environmental conditions will be in future. But in this presentation, I'm not considering very delicately those future conditions, but given the current scenario, I'm predicting what could happen and what we should be doing in future. So corrosion is a slow action, and it is like cancer as opposed to an accident. Here you can say an earthquake or a flood, all these are accidents which acts on us immediately and has a huge impact, whereas corrosion is a slow process and like a cancer. But we have to do something before we get the cancer, or at the early stages of cancer, otherwise it will be very dangerous. So that's the analogy which I thought will be a very useful analogy to think and to give importance to this corrosion mechanisms. Now, what are the exposure conditions? They are very severe today and may become more severe in future. Seawater level might rise, and there will be tidal variations which may cause change in the spray and wet dry zones on the concrete elements. For example, if you take the picture at the bottom left, which is a bridge which is standing on seawater, if there is a tidal level variations, there may be portions of the concrete which were not or which are not exposed to chlorides today, but may become more severely exposed to chlorides in future. So that is a structure on the on seawater. But then if you are talking about very near the coastal region, there may also be other reasons by which chlorides can attack more severely to the structure. So one is storm surge or flood, and this can also, if you have more frequent in events like this, then that can also mean more frequent chloride attack to the concrete structure, and also proximity to the shoreline. It can increase both airborne and soil-borne chlorides. So if the seawater level rises, definitely the currents today, if the structure is X kilometer away from the seashore, it might be X minus something kilometer away from the seashore in the decades coming. So that's a serious thing. So how do we keep coastal structures safe for several decades? And we are not talking about 1 or 2 decades here. We are talking about maybe even close to a century or more. So how do we keep such structures for several decades ahead with minimal maintenance and repair? So for now doing that, first thing we need to know is what is service life, or how the service life mechanisms are. So the sketch on this, let's see if I can, the sketch here, you can see what are the parameters which really influence the service life. First one is cover depth. Definitely you have to have a good cover depth, and that will definitely ensure long service life. And if you are looking at material parameters, is the surface chloride concentration. That means not necessarily material, but near the material surface or the concrete surface. That's essentially an exposure condition dependent. And then if you look at material parameters, you have this diffusion coefficient of the chloride, and how that diffusion coefficient can change as a function of time with new materials in market, and also the chloride threshold, which is a function of the steel and the concrete interface. So these diffusion coefficient of the chloride and chloride threshold, they really influence at what time corrosion can initiate. That's this point here, the blue circle which you see, that is the time at which the corrosion initiates. And if you look at this graph, the length of the blue region is much more as compared to the length of the orange region, which is the red region, which is the propagation phase. So if you want to extend the life of a structure, the important or the most crucial strategy would be to extend the life of the initiation phase. That is, extend the length of the blue line here. That means we have to have concretes which are having very low diffusion coefficient. That means very high resistance against chlorides, and at the same time very high chloride threshold. That means it needs more chlorides to initiate corrosion. So material properties of concrete and steel and the cover depth can influence the service life of concrete structures. All these are very important. So how do we use these parameters to determine the service life? There is a fixed second law of diffusion, is widely used mechanism, or widely used phenomenon. And then here we have made this nomogram, which is using those principles. We made a simple tool which a practicing engineer can easily use to do some preliminary estimates of service life. So main objective of this is, once you know that, okay, the structure which I'm going to build should have a let's say 100 years or 50 years of service life, then we can use this nomogram and start from the design parameters like cover depth D or the probability of failure or probability of corrosion initiation at the desired service life. That is, if we are designing for 50 years, at 50 years, what should be the probability of corrosion initiation? Then these two parameters a structural design office can determine, and then the materials engineer can also decide what type of binders and steel should be used. Okay, zone 2 here. So you can do from here A to B point and then B to C. We can say, okay, I'm going to use OPC or fly ash or slag-based cement. There are different combinations. So based on that, you can pick one of these inclined lines, and then you go down from point C to point D, which is saying based on the selection of E. So if you want about, in this case, about 25 years, this example I'm talking, then you can say which D curve you have to pick, which is at the bottom right. And then based on that, you can say, if you want this much design, this much of service life, then you have to use this much cover, you have to use this cement type, and you have to use this steel type. And at the site, you have to ensure that the diffusion coefficient of the chloride is based on, is the, as per the target design, target diffusion coefficient. So that's the beauty of this. From the structural design office to the materials engineer to the field engineer, it's all dependent, then we get a service life. So we have to really look at the synergistic effects of various parameters of both steel and concrete, and then only we should choose the material combinations and specify, instead of usually we specify concrete grades only, the strength grades only, but we are suggesting to specify the durability grade also along with the strength grade. So that's what we are proposing, like MXDY mix, instead of just the strength grade mix. So this is the crux, I mean, the essence of this nomogram and how it can be used. Now we design structures with this, and then if we don't really care about the field conditions and all that, then you may end up in having very severe cases. So what is the ground reality and what is the need, which need of the hour? So some concretes are exhibiting less resistance against chlorides than expected, and higher chloride diffusion coefficient is the reason than expected. So, and also some steel reinforcement systems are exhibiting less resistance against corrosion because they have a lower chloride threshold than expected. So these can lead to significant reduction in the service life than as per the target or desired service life. So reality is probably in some cases far away from the design expectations. So what do we need to do to avoid these problems, especially for the structures which are already there today? I'm in this remaining rest of the presentations, I'm really going to focus on existing structures, not new structures. Of course, this can be applied there also, but let us, I'm mainly focusing here on existing structures. So what we need to do is testing relevant material properties using correct test procedures. That's very, very important, because we have seen many places test procedures adopted are not really representing the system. When you borrow ideas from some other earlier procedures, it doesn't really work. And they should also be done on the field specimens rather than a specimen which is applied by the manufacturer of the material and also cast with very high quality control in the laboratory. So you have to really mimic the field conditions, and these are very, very crucial when we talk about estimating the residual service life of the structures, in particular the existing structures. So what are the adaptation strategies, or the strategies to make sure that these structures can be resilient in future or slow down the deterioration process? Now, it's like the medicines which you are giving. Once the cancer is known, so once you think that there may be potential, tumors or etc. like that. Now, the coating of concrete surface is the first thing which we can do. This sketch here is familiar to you. So these red bubbles which you see here, circles, are the chloride ions, and the black circle at the bottom is the steel bar, and the blue arrow indicates the chloride diffusing towards the steel. So what we can do on an existing structure is provide a coating. That is the green rectangle which you see at the top. Then another option is provide cathodic protection, which is an electrochemical way of protecting the structure from corrosion. Okay, so this is, you can see zinc, and then this basically cathodic protection, you attach a zinc metal to the steel, and that will help in preventing corrosion or arresting the corrosion process. And also you can do electrochemical extraction, which is the blue arrow here at the top, which indicates whatever chlorides have entered into the concrete, you can probably apply some electrical current and extract those chlorides out of the concrete. So these are the key procedures which we can adopt to enhance the resilience of concrete structures which are exposed to chloride conditions. So now we will look at how the selection of these strategies will definitely depend on the type of steel reinforcement which you have and the condition of the structure at the time of repair. So what are the steel reinforcement you are going to look at is uncoated steel and FB or fusion bonded epoxy coated rebars, and also looking at the pre-stressing strands or pre-stressed strands rather. So we'll show a case study. Before that, I'm going to talk about where these structures are used. You can see these images where all these fusion bonded epoxy coated bars are used, and you can see a lot of cracks or damages. You can see rust spots on these pictures, and these are exposed to sunlight because of the delays during the construction, and that means exposure to UV radiation. So these type of coated rebars, unless you handle them with care, they don't perform well. So these are the cracks which we have seen on the samples which are actually used at the sites. You can see severe cracking due to bending after the coating, and then it's also very rough handling of the rebars. There's a lot of cracks, and also when you expose this rebars to sunlight for about a month or 45 days, you can very clearly see that there will be cracks which will lead to crevice corrosion, which is very dangerous, and that can happen even without very limited amount of chlorides. So also we have pre-stressed concrete structures. A lot of them are being built today. For example, here you can see in 1950s, there were only 20% of the concrete bridges were of pre-stressed type, where today you are talking about 80+% of pre-stressing are used in concrete structures. So this is also very, very important. Now this is a case study I'm going to show how we can adapt the resilient or the remedial measures to enhance the resilience. We took a typical structural element, which is actually in the coast, just 2 kilometers away from the shoreline in a major city in India. And we looked at this. You can see the different type of rebars, because this structure had all these 3 in that structure, and they have different various elements. And also we took concrete core from the structure to actually determine the diffusion coefficient of the concrete which is actually used, not from the specimens made in the laboratory. So this is more realistic. And so what we found is the chloride threshold of the uncoated bar, if it is 0.4, there is significant reduction in the chloride threshold of the epoxy coated bar, which as these first 3 red arrows indicate that significant reduction. And in the case of pre-stressing strand, again you have the average value. If it is unstressed, it is 0.4, but if it is pre-stressed, that is the reality, it's much lower than the unstressed, that is about half of it. So this, what we should be using for residual life estimation is the markers which are shown below the red arrows and not the black ones which are at 0.4. So we have to really use the realistic or closer to the reality chloride threshold values. And also now effect of surface coating is what I'm going to show. If you're talking about an uncoated rebar, you have the uncoated rebar here, and the green line here indicates if it is very perfect rebar which is used, and if the rebar is used, and if you apply a coating at about 10 years, So the first coating, if you apply at 10 years, you can significantly enhance the life from about 25 years to about 150 plus, if it is applied at about 10 years. But again, here in this study, it's a preliminary study, so this all green range is there. That means the degradation of the coating, and also we have assumed that the coating will degrade in 10 years, but every 10 years you will have to redo this coating. So that's the trouble, or in going with this methodology, is that every 10 years you have this repair procedure or this remedial measure to be taken up. So on the right graph, if you see, if you apply a coating at the 10-year and every 10 years after that, you can really extend the life of the structure. But if you wait until that corrosion starts, if you don't apply for 30 years, then extending the life to 100 plus years is not really possible unless you go for cathodic protection. So this cathodic protection is very, very useful. ICCP, we have to worry about vandalism and things like that. So SCCP, or the sacrificial anode or galvanic cathodic protection system, is recommended for these type of bridges which are far away from the cities and etc., where there is nobody to monitor. So in such cases, we can go for the cathodic protection. And you can see this blue curve here. Once you repair, you can really keep this concrete or the steel from corrosion, from no corrosion. It will not corrode, or we can maintain it for as long as we want. So that's the beauty of it, at least for the desired life. You have to keep replacing them, but it is only about once in 20-25 years you have to do that. Now for coated rebars also significant reduction. We did the similar study. You can see the distribution on the left side where the probability of corrosion initiation is shown. If you don't do anything to these structures, for the case study which we did, this will start corroding it in about 20-25 years. And if you apply the coating after 5 years, then you can really get the life to very close to 100 years. If you apply after 10 years, you can extend the life to 50 years. But again, it's every 10 years you have to keep doing that coating. So, but again, in the case of epoxy coated rebar, the message is apply the apply the surface coating as early as possible. Otherwise, we will have severe trouble. Similarly, for the UV exposure case also, we see very significant reduction.
Professor Pillai, can you please wind up? You have exceeded your time.
Yeah. So as seen on the screen, the message is applying coating as early as possible. It's very, very important. Now for the for the epoxy coated, there are technical challenges with applying epoxy cathodic protection to this. This need to be studied. For the pre-stressed concrete, you can see that again significant reduction. Look at the right side curve. You can see if you do not. So the message here is if you do not apply the surface coating before the corrosion initiation time, then it's very, very difficult to enhance the service life of the structure. So the action has to be taken as early as possible. Again, for the cathodic protection, it is possible for pre-stressed concrete structures. So if you are able to detect the corrosion before it is initiated, we have procedures to actually extend the life. To conclude, you can see here on the uncoated rebar case, what is the condition? If you have high chlorides in the cover concrete, with or without corrosion, cathodic protection is possible. Okay. And if it is very minimal, that is very early action if we can take, then surface coating is probably sufficient to extend. But at the same time, because of the frequent repair required, then it is better to go for cathodic protection. For the coated rebar system, in the similar case, the cathodic protection is very challenging to apply, but surface coating is possible, but you have to really go for very frequent applications, like every 10 years, you will have to apply the surface coating. For the pre-stressing strand, again, similar way, because it is no coating there, you can really go for cathodic protection, and each cathodic protection system can be designed for a life of 25 plus years. And if it is a surface coating, our procedure we are going for, then every 10 years you have to keep doing it. But again, the main point is if you go for surface coating, you have to really act as early as possible. Otherwise, the effectiveness is very, very minimal. So the main message is apply the surface coatings if it is, in a chloride environment condition for these coated rebar system and pre-stressing strand systems as early as possible, especially before their corrosion initiation, which can be determined using the nomogram, which I mentioned earlier. I think with that, I will stop. Thank you. These are the people who are helping us in doing this research. Thank you. Professor.
Okay. So appreciate your talk on the very interesting topic. And then there are many questions from the YouTube, and due to the time limitation, I will ask some. First interesting question is about to make the RC member chloride corrosion resistant, which one will be the preferred economically to go to the market, go to making steel rain resistant or concrete resistant, such as by making impermeable concrete? So which one do you think is better in terms of the economic benefit to choose steel resistance or concrete resistance against chloride?
I would suggest, if the concrete can be made better, and if you can ensure adequate cover, there's nothing better than that.
Okay, so that is very wise answer.
Yeah, I was talking to Professor Kessler in Germany, and she was saying they have studied actually epoxy coated rebars in the field, and they found that they perform better if the concrete is very good. But in such case, if the concrete is very good, you really don't need epoxy coating.
Right.
So main point is, if you use epoxy coating, we have to handle those steel like babies. They're very,
yes.
They have to be handled like babies. Otherwise, it's better to invest that much energy and efforts in making the concrete better, more chloride resistant.
Okay. So next question is, how about the structural elements or parts of concrete structure completely submerged in water?
Can you repeat?
Concrete on the water. What is the chloride diffusion behavior of concrete on the water? You mentioned about the offshore structure, onshore structure.
Yeah, I think that it's more critical to look at the concrete at the spray zone or wet-dry exposure conditions. As you go deeper, let's say a couple of meters below the water level, there you may not see much corrosion because of the lack of oxygen there to sustain corrosion. So it's more important to look at the diffusion coefficient of the concrete near the water level and use that number for estimation of service life and things like that.
Okay, so I see more questions, but I think you can, if you have time, you can chat on the YouTube.
Sure.
Then they can understand the situation in terms of the time limitation. Thank you very much for a very interesting talk on the resilient concrete, especially for the design of service lives depending on the different conditions. So thank you very much.